Okay, so this is the last lecture of the day, and the speaker is Anne Schilling. She will talk to us about Plethysm and the algebra of uniform block permutations. Okay, Anne.
Thank you so much for the invitation and to the organizers for organizing this conference. Since we had a day yesterday for Dick Askey, I just wanted to briefly say that I met him also at a lot of conferences. And the last time I actually saw him was at an AMS sectional meeting in September 2019, where the family brought us to where he was. And it was a very touching moment. So that was the last time I saw him. Anyway, so now let me talk about Plethysm and the algebra of uniform block permutations. So this is joint work with Rosa Orellana, Franco, Saliola, and Mike Zabrocki. And I want to start out by first telling you what the Plethysm problem actually is and how it's related to orthogonal polynomials. Let me start with that. And I'm going to start very basic. So let's first consider representation theory. So when you have a group G, then for a representation, you usually consider a vector space V. Then the representation is a map from the group to the endomorphisms of V, of this vector space. And then when you have such a representation, you can look at the characters, which are just given by the trace of rho of G. And one thing I would like to remind you of, which is very well known, is that characters are class functions, meaning that if you look at conjugacy classes, then the character is constant on these conjugacy classes. And the reason why I'm mentioning this is because later in the talk, we will actually generalize this to semigroups. So for a semigroup, you don't have an inverse for every element anymore. And in that case, we are also going to look at representations and characters, but the characters won't, the notion of the conjugacy classes will be slightly different. Now, let's look at the specific case. So let's look at the invertible n by n matrices, let's say over the complex number, so GLNC. And what we can do is we can look at, let's say, two representations. The first one would be a GLN representation, which goes from the group GLN, right? It's invertible matrices, so it forms a group, to GLM. So you can also think of GLM as endomorphisms, right? On the vector space C to the M. So that's why this would give you a representation. And then we can look at the second representation, let's call it tau, going from GLM to GLR, okay? And once you have that set up, we can compose these two representations. So we can look at the composition, and the composition would go from GLN to GLR. We can look at the characters of this composition of representations, and that's precisely what the Plethysm is. So you look at the character of the composition of these GLN or GLM representations. That's the definition, but I actually want to get to symmetric functions. And the way that that's usually done is via the Frobenius map. So we saw that the characters are given by their class functions. So let me call Rn the space of class functions of GLN, and lambda n the ring of symmetric functions of degree n. There are various bases for the ring of symmetric functions. So for example, we have the power sum symmetric functions, p lambda. So p lambda, where lambda is now a partition. So a partition is a sequence of integers, lambda 1, lambda 2, up to lambda l, that are weakly decreasing. And p lambda is just the product of the p's for the various parts in the partition. So p lambda 1, p lambda 2, p lambda l. And if you just have a single part, pr, that's just the sum of the variables x1 to the r plus x2 to the r, and so on and so on. So we are working in infinitely many variables. That's one basis. Another famous basis is the basis of Schur functions, also indexed by partitions lambda. And there are various ways of how you can define them, but a combinatorial way to define the Schur functions is by summing over all semi-standard Young tableau of shape lambda. So what is a semi-standard Young tableau? Well, you take your partition and you just fill it with numbers, such that in every row, the numbers are weakly increasing, and in every column, the numbers are strictly increasing. And then you take x to the weight of this tableau. So really what this means is x1 to the number of ones in the tableau, x2 to the number of twos in the tableau, and so on. So that's a Schur function. And on the ring of symmetric functions, we also have the Hall inner product. And under this Hall inner product, the Schur functions are actually orthonormal. So S lambda, S mu, the inner product of those is 1 if and only if lambda is equal to mu, and otherwise it's 0. So how do we go from the class functions to the ring of symmetric functions? Well, we can define this Frobenius characteristic map, which takes a class function chi and maps it to the sum that you can see here. So here the p mu are the power sum symmetric functions. Chi mu is just this class function evaluated at mu. And then this C mu is something that is very familiar in representation theory. So that's the size of the stabilizer. So if mu is the partition where you have A1 ones, A2 twos, and so on, it's just, this product. And if you look at the irreducible characters, they're indexed by, again, partitions. So let me call an irreducible character chi lambda. Then under this Frobenius map, this irreducible character is actually mapped to the Schur function. And this is true because we have this identity between Schur functions and power sum symmetric functions. So I started off by telling you what plethysm is in terms of representations. So now under this Frobenius map, let's see how that pulls over to the ring of symmetric functions. So suppose we have two symmetric functions, f and g, and suppose that we know the monomial expansion of f, let's say. So this means we know that this is a sum of certain x's. So when I write x to the ai, I really mean x1 to some power, x2 to some power, and these powers are sort of captured by this vector a upper I. Okay, so we suppose that we know this. And if you know the monomial expansion of f, then the plethysm of g of f is actually, or you can work it out, or you can define it this way, by taking g and now evaluating it at the monomials of f. So usually g would be a symmetric function, so it would be g of x1, x2, x3, and so on. But now instead of x1, we're actually inputting xa1 and so on. And plethysm, just as a slight remark, is actually Greek for multiplication. So in our case, it's actually really composition. A couple of simple examples. So let us take the Schur function S1. S1 is just x1 plus x2 plus x3 and so on. So if we want to look at the plethysm of G, plethysm S1, well, we have our monomial expansion here, and by that definition, we just evaluate G at the monomials, but in this case, the monomials are really just the variables. So in this case, G of S1 is nothing else but G itself. And here's another simple example. So we know that the power sum symmetric function Pn is x1 to the n plus x2 to the n and so on. So if we want to compute the plethysm f of Pn, Well, now we have to take f and we evaluate it at the monomial. So we evaluate at x1 to the n, x2 to the n, and so on. But this would just be if we still use that f has this monomial expansion as above, this would be just this sum where we just multiply every power by n, and that's also equal to Pn of f. So these are just two simple examples of how you can compute plethysm on symmetric functions. I want to give you a slightly more complicated example because that will actually give us some intuition of what the combinatorics is that comes into play. So let me look at the Schur function S2 in just two variables, okay? So our definition was that we sum over all semi-standard Young tableau of shape 2 in this case, because our partition here is just 2. Okay, so here are my shapes. And since we have two variables, I am going to fill this by just ones and twos. And remember that we have the condition that in rows, the numbers have to be weakly increasing. So in this case, we actually only have 3 semi-standard Young tableau of shape 2 that you can fill with the numbers 1 and 2, namely 1, 1, 1, 2, and 2, 2. And the corresponding monomials are just x1 squared because we have 2 ones in here, x1, x2 because we have a 1 and a 2, and then x2 squared because we have 2, 2. Now what I want to compute is the plethysm of S2 of S2, but in two variables, I mean in x1 and x2. Our prescription was take the outer S2 and evaluate it at the monomials of the inner S2, and the inner S2 had the monomials x1 squared, x12, and x2 squared. So this is what we have to compute. Now again, we now have 3 variables, right? Because we have 3 slots filled. And what we now have to do is look at all semi-standard Young tableau, again of shape 2, but now in 3 letters, because we now have 3 variables. And these are all the tableau that you can get. 1, 1, 1, 2, 1, 3, 2, 2, 2, 3, 3, 3. Okay. And but now notice that the 1 in an entry really corresponds to a 1, 1 if you look at the expansion up here, right? Because the variable in the first slot is really an x1 squared. So what you have to do is really take the tableau that corresponded to the x1 squared and put it for the 1. So what you can see in the second row is really a sequence of tableau, right? So they are still of shape 2, but now instead of putting just numbers into every slot, we now put 2 numbers in there because, or again, a tableau of shape 2, which came from the inner Schur function S2. If you look at the first entry, so here we have 4 ones, so therefore the monomial that you get is x1 to the 4. In the second case, we have 3 ones and a 2, so you really get an x1 cube, x2, and so on and so on. So you get the monomial expansion that I've written up here. And then you can just observe that all the terms in green are actually correspond to the Schur function S4. And then the term in red corresponds to the Schur function S22. So this plethysm of S2 can be expanded into Schur functions S4 and S22. And one thing that you notice in this nice simple example is that all the coefficients have non-negative integer coefficients, right? And this is actually true in general. Namely, if you take the plethysm of a general Schur function as lambda with S mu, and you expand it again in terms of Schur functions, if you look at the coefficients that are there, which I call A lambda mu nu, then these are all non-negative integer coefficients. And well, as a combinatorialist, you're interested in finding an interpretation for these numbers, right? You would like to find a set that counts these numbers. So for example, if you take the product of two Schur functions and you expand in terms of Schur functions, you would get the Littlewood-Richardson coefficients, and we have a combinatorial interpretation for those, but we would also like a combinatorial interpretation for these numbers. And that in general is still an open problem. But I hope I convinced you from the previous slide that if you at least look at the monomial expansion, really what you are looking at are tableau of tableau. So you have tableau, but then in each entry, you also put a tableau. And one way to actually get a Schur expansion for such objects would be by finding a crystal graph on this. And we have tried very hard to find a crystal graph on these tableau of tableau, and this seems like a very hard problem. But what I want to show you in the rest of the talk is some other techniques that you can use to hopefully make some progress on this problem. Okay, so first of all, some cases of this problem are actually known. So I'm just going to give you a couple of like special cases. And to give you the formulas, I just need a couple of definitions. So I'm going to call a partition even if all columns have even length. So for example, here, I've written down the partition 2, 2, 1, 1, right? So that's a Young diagram for this partition. But you can see that the first column is of height 4 and the second column is of height 2. So I would call this partition even because the columns have even length. Similarly, I'm going to call a partition threshold if you look at the transpose of the partition. So I'm going to denote the transpose by lambda prime. If lambda I is equal to lambda I plus 1, or in terms of a picture, here you can see like the green part, and the green part, if you look at the green part and you sort of transpose it, then you can see that the white left over looks exactly like the green part. So this is precisely what this condition is saying. And there's a theorem which actually gives a very nice combinatorial interpretation for the Schur expansion of the following plethysms, namely S of a single row, so SH of S2. You can write this as the sum of all Schur functions where the transpose is an even partition. And similarly, if you take S1 of a column, so S1 to the H, S2, then this would be the sum of all Schur functions where the transpose is threshold. And similarly, if you take SH of S1 squared and S1 to the H S1 squared. I would say that this is actually not a new theorem. This has appeared in a Littlewood's paper in 1950. And you can also look at MacDonald's book. On page 138, he also gives these identities. But the proof that both Littlewood and MacDonald give is actually quite complicated. So one thing I would like to sort of advertise here is a new way of possibly proving such identities. Oh, and yeah, so before I do that, here's like a picture of both Littlewood and MacDonald. So the way to prove this that I would like to advertise is what I call the s-perp trick. So what is the s-perp trick? So there is an action of what is called s lambda perp on a symmetric function f, and it's defined as follows. So it's defined as, so the bracket is still the whole inner product. So you take the whole inner product of f with a product of two Schur functions, and you expand it in terms of S mu. And combinatorially, so if you think of this on a Schur function, basically what this perping is doing, it's skewing by lambda. And one thing that you can immediately sort of see, yeah, there's a question.
Yes, is it the same as differentiating?
I think probably in terms of power sums, it would be.
Yes, that's what I mean.
Yeah, yes, yeah, I think that's correct. In terms of Schur functions, I'm not sure how to actually formulate it in terms of derivatives. So that's why I've formulated it this way. In any case, so one thing that you can see is if you have two symmetric functions, f and g, and let's say they're both of homogeneous degree d, then suppose you know that s-perp on f and s-perp on g, so SR is now just like a single row. And if that's true for all r between 1 and d, then the two functions are actually equal to each other. Okay, and the same is true if you replace s-perp by a column, so s1 to the r-perp. Okay, and so the reason why I mentioned this is because for this plethysm problem, there are actually very nice formulas of s-perp on a plethysm. And I've stated them down here. So s-perp on s1 to the h, s1 to the w is equal to a product of two plethysms. But as you can see, they're sort of a smaller case. Namely, if we start with the column of height h, then here you have like a column of height h minus r. Or if you look at the second term, right here, we are taking the plethysm with s1 to the w, but then in the second term, we have s1 to the w minus 1. So you can sort of see that these formulas can be used to recursively prove formulas. And so we've actually given a very nice proof of the formulas that I've just shown you using this s-perp trick. And we also have generalizations of combinatorial formulas that we are not aware of have appeared in the literature yet. A nice way of proving these identities. Okay, but as I said, so this problem is still wide open and it seems very hard to attack otherwise. Oh yeah, before I go on, so one benefit of doing this s-perp trick is that it actually also gives a very fast algorithm to compute plethysm. So I work a lot with Sage, and if you try to compute the plethysm, it often, like if you go to partitions, let's say of size 5, it actually takes quite a long time. It can take like 30 minutes to actually compute the plethysm, but using this trick, it actually gives you a much faster way of computing them because you can use recursion. So since this is a kind of very hard problem, one thing that we've been thinking about with my collaborators is to get some inspiration from, again, representation theory of how to attack this problem. So now we are going to sort of take a random walk. I've laid out for you what the problem is, but we are now going back to representation theory and some other first seemingly unrelated kind of things. And then our random walk will take us back to the plethysm at the end of the talk. First of all, I would like to mention that the plethysm is actually also related to what's called the restriction problem. Namely, if you have a GLN representation, Sn, right, the symmetric group sits inside GLN. And so you can look at the restriction of the representation of GLN to Sn. And if you do that, well, it will decompose into irreducible representations of Sn with some multiplicities, which here I called R lambda mu. But it turns out that these coefficients, R lambda mu, can actually be expressed also in terms of plethysm, namely the plethysm of this Schur function that I have written down here. But now, yeah, so now we are going to shift gears to something that first seemingly seems very unrelated, but as I said, we will walk back to the plethysm at the end of the talk. So I want to talk a little bit about diagram algebras. So what's a diagram algebra? So we've just talked about this restriction, right, of GLN to SN. And well, if you look at V, so let's say V is C to the N, right? GLN acts on C to the N, but now you take a k-fold tensor product of that. You have a diagonal action of GLN on V to the K. You can restrict this to Sn. So basically, if you have a permutation sigma, it would just diagonally act on such a k-fold tensor product. And one question that you can ask is what commutes with this action? So if you think about Schur-Weil duality, right, usually we have GLN acting on such a tensor product V to the K, and the action that commutes with that is the action of SK. So in this case, when we restrict, we can also ask what commutes with this. And the answer was actually given by Martin and Jones in the 1990s. Namely, this is the partition algebra, which I call PK. Let me just say a couple of things about this partition algebra. So the basis of this algebra is the set of all set partitions of the set from 1 up to k, and then a duplicate of this, so 1 bar up to k bar. And we can actually represent these in terms of certain diagrams. So for example, here I have a set partition, right, of where k is equal to 8. And what you do to get a diagram is you write the numbers 1 up to 8 in the top row, 1 bar up to 8 bar in the bottom row. And then whenever two numbers are in the same block, then you connect them. So for example, here we have 1, 2, 4, 2 bar, 5 bar in one block. So in this diagram, 1, 2, 4, 5 bar, and 2 are connected. Okay, so that's how you can go from set partitions to these diagrams. It's a picture of Martin and Jones. So what we can now look at are what are called centralizer pairs. So we can look at representations of this diagram algebra, of the partition algebra PK. And one thing that is known is that the dimension is actually the number of what are called set value tableaux. What Jones proved is that sort of an analogy with Schur-Weil duality, V to the kth tensor product can be decomposed into Sn representations and PK representations. And so now we basically have sort of two centralizer pairs, namely the usual one that you get from Schur-Weil duality, where GLN acts and the centralizer is SK. But if we restrict GLN to Sn, we have another centralizer pair, namely in this case, it commutes with the diagram algebra PK. Well, then you look at this, and so when we try to understand this in more detail, we ran into this book by Goodman and Wallach, Symmetry, Representations, and Invariants. And one thing that they discuss in this book is what are called seesaw pairs. So suppose that you have an algebra A, which is embedded into an algebra B. Setup is you can look at representations of this algebra B and restrict it to A. This is exactly what we have been doing, right? We took GLN and we restricted to Sn. And then we get these multiplicities. If we decompose this into irreducibles of the algebra A. Suppose that we have two centralizer pairs, which we have in our setting, right? So we have an algebra A embedded into an algebra B, an algebra C embedded into an algebra D, but B and C form a centralizer pair and A and D form a centralizer pair. Then what Goodman and Wallach write in their book is that the indices for the simple modules for B and C are in fact the same, and also the indices for the simple modules for A and D are the same. Therefore, and in particular, if you now take an irreducible representation for D and you restrict it down to C, then these coefficients that you get are actually the same as for the restriction from B to A, are actually related to each other. So now let's take this back to the setting that we were looking at, where we are acting on the k-fold tensor product of V, and we have, well, GLN acting on this. We also have SN acting on this, and then we have SK, which forms a centralizer pair with GLN, and then we have PK, which forms a centralizer pair with SN. Okay, and what we gained from this general theory that Goodman and Wallach describe in their book is that, well, if we restrict GLN to SN, then the coefficients that you get, these R lambda mu, these restriction coefficients, are actually, they also pop up if you look at PK restricted to SK. Some good knowledge. And remember that these coefficients were also related to plethysm, the problem that we are actually interested in. The idea is now that we can look at PK, this diagram algebra, to get a handle on the plethysm problem. What we really want to do is restrict to SK, to the symmetric group. But instead of doing that, what we are going to do now in the next couple of slides is actually go to an intermediate algebra. And this intermediate algebra is what we call the uniform block permutation algebra, which I denote by UK. The good thing is that, well, if you take PK and you restrict to UK, you actually get some sort of generalized Littlewood-Richardson coefficients. But if you look at UK restricted to SK, you get special cases of plethysm. So we have sort of broken down our problem into smaller pieces. The plan is for the next couple of slides. We are now going to look at this, the subalgebra UK. Okay, and then what we are interested in is we want to get some combinatorial model for the representation theory of UK. Describe for you what this uniform block permutation algebra is. So this actually is a special case of an algebra that appeared in papers by Tanabe and Kosuda, which they called the party algebra. And actually the reason why they called it the party algebra is because suppose you have two parties and then you have subcommittees of those parties that discuss certain things, let's say like foreign policy, taxes, and so on. But for every committee, you want the same number of people from each party, right? So the committee on taxes should have 5 people from party A and 5 people from party B. That's why this is called the party algebra. And so now let me be more specific of how we actually define this mathematically. So remember that we were looking at set partitions, right? For the diagram algebras of set partitions of the numbers from 1 up to k and 1 bar up to k bar. And we call such a set partition uniform, well, if in every block, the number of barred and unbarred letters is the same. So if that is the case, we call the set partition uniform. So here's an example. Here we have a set partition where k for me is now equal to 9. But you can see that for every block, we have the same number of barred and unbarred letters. So for example, the first block contains a 2 and a 4, and we have 1 unbarred letter, the 2, and 1 barred letter, the 4. But if I look here later, we have a block 4, 6, 3 bar, 6 bar, and again, we have 2 unbarred and 2 barred letters. So therefore, this is actually a uniform set partition. And when you have such a uniform set partition, you can actually think of it as a size-preserving bijection. Namely, you can look at the unbarred letters, and the unbarred letters are mapped to the set of barred letters within each block. So again, if we look at 4, 6, 3 bar, 6 bar, right, you can think of 4, 6, the unbarred letters being mapped to 3 bar, 6 bar. Okay, so we have these various ways of looking at these. Therefore, we also call the elements of the uniform block permutations, we call them uniform block permutations because they sort of permute blocks of the same size. So here would be a diagram for a particular uniform set permutation. Okay, so we do it the same way as before. We connect all the letters that are in the same block. Well, you can take products of such objects, of such diagrams. So if you have a D and a D prime, what you take the product by just stacking them on top of each other and then just looking at the connected components that you get. So remember what I wanted to do, what we set out to do. We wanted to understand the representation theory of these uniform block permutations. And one thing that is very important to understand the representations are the idempotents in this algebra. So let me now define for you the idempotents in this uniform block permutation algebra. Namely, now we just look at set partitions not of 1 up to k, 1 bar up to k bar, but only of the set from 1 up to k. Okay, so I call that pi. And then I'm going to define e pi to be the set partition that contains the set partition of A and also the same numbers, but all barred. Okay, so A bar is just the analogous barred letters. So here would be an example. Here I've written down just a set partition of the numbers from 1 up to 9. And then you can see that the top and the bottom have the same set partition, right? So for example, here 1 and 4, they're connected on the top, but they're also connected on the bottom. So those are called e pi. And by that product that I've just defined you, so if I stack the e pi on top of another e pi, you can very easily see that you get e pi back. Okay, so therefore this is actually an idempotent. And one thing that we proved is that these are in fact a complete set of idempotents. So one other thing that you can notice about this uniform block permutation algebra is that this is actually what's called a factorizable monoid. So what does that mean? So here I've written down some sort of arbitrary element, which is a uniform block permutation. And when I say it's factorizable, it means that I can always factor it as an idempotent times a permutation. So you can see that here in the second one, I have an idempotent on top, and then I have a permutation on the bottom, right? So a permutation in the setting, in this uniform block permutation setting, is just all the blocks are of size 1. Right, and here, so for example, 1 is mapped to 3, 2 is mapped to 1, and so on. And by the way, this works in both ways. So you can write it as an idempotent times a permutation, or a permutation times an idempotent. One thing that we proved is that for any element D in this uniform block permutation monoid, you can always write it as an idempotent times something in the symmetric group. Okay? And then once you realize that you have this nice setup, then we actually ran into another very nice book written by Benjamin Steinberg in 2016. So he developed the representation theory of finite monoids, and in particular of factorizable monoids. So again, we can sort of draw from the big theory that has already been developed in our special setting. And one of the things that you learn is that the representation theory of your monoid is actually governed by the representation theory of what are called the maximal subgroups. And the maximal subgroups are all indexed by the idempotents. Okay, and so in our setting, the maximal subgroups, again, they are now indexed by these e pi, because the e pi for us are the idempotents. And they are all elements such that the top and the bottom, so the top permutation, the top set partition and the bottom set partition in these diagrams are equal to each other. So here would be an example. If pi is equal to the set partition, then this would be the maximal subgroup, right? So you can permute the blocks of size 1, and you can permute the blocks of size 2, as you can see here. And in fact, this is true in general. So if you have pi given by A1 blocks of size 1, A2 blocks of size 2, and so on, then the maximal subgroup is always isomorphic to a direct product of symmetric groups. So SA1, tensor SA2, and so on. Okay, so that's very nice. And in particular, what that tells you is, since the representation theory of our monoid is related to the representation theory of the maximal subgroups, well, we know what the representation theory is of the symmetric group, right? They're indexed by partitions. So in our setting, we now know that our representations are indexed by tuples of partitions. Okay, so tuples lambda 1, lambda 2 up to lambda k. So that will be our indexing set. So here's an example. If k is equal to 3, we want all tuples of partitions such that this weighted sum of the sizes of the partitions adds up to 3 in this example. So in the first slot, you can put in all partitions of 3, which are 3, 2, 1, 1, 1, 1. Or you could have a partition of size 1 in the first slot and a partition of size 1 in the second slot. Or you can, so which is this one, or you can have just a partition of size 1 in the third slot. So those would be the things that index our representations. And well, again, if you know something about the representation theory of the symmetric group, you know that that's governed by standard Young tableau. And so for this uniform block permutation monoid, they are actually governed by tuples of standard Young tableau, where the first one is just a standard Young tableau, and the second one, in fact, you enter tuples, so you enter subsets of size 2, and the third slot you enter subsets of size 3, and so on. And the irreducible representations are given by the span of these tuples of standard Young tableau. So here would be an example. If we take this example of 1, 1, then we take these tuples of a tableau of shape 1 and shape 1, but in the first one you put just one number, and in the second one you put 2 numbers. Okay, so that's how you get the representation theory. And remember, in my very first slide, I told you that for groups, characters are class functions. So it turns out that for monoids, characters are also class functions, but for a different definition of conjugation. And I don't actually want to go, for time reasons, through the details, but basically what you get is, if you think of x and x prime here as in a group, as inverses, then this would be exactly the same notion of conjugacy. But for a monoid, this, or a semigroup, this actually becomes more complicated. So for these maximal subgroups, we also have the notion of a cycle type, right? So for the symmetric group, our cycle type would be how many cycles do you have of a given length. So here we have indexed everything by tuples. So our cycle type now is actually a tuple of partition. And one thing, again, that you learn from reading Steinberg's book is that, so the characters of a monoid, so in our case, the character of the monoid UK is a sum of the characters of the maximal subgroups. up to some coefficients, which we call here b mu nu. Okay, and so you can write these as sums of characters of just groups. And in fact, we have a very nice formula for these coefficients, again, in terms of generalizations of these centralizers, sizes of the centralizers, these z lambdas. Okay, and in the last couple of minutes, I want to sort of loop back now to how this is related to symmetric functions, because as we've seen in the beginning, characters under the Frobenius map can actually be mapped to symmetric functions. So since here we have always tuple of things, we actually now have symmetric functions on multiple variables or multiple sets of variables. So x1, x2, x3, but x1 is really a set of variables. And now we have to define a polynomial ring. So we take our power sum symmetric functions, but we have to take our p's, but in terms of these various variables also, or variable alphabets. Okay, so the first line is just our usual power sum symmetric function and the alphabet xj, but then in the set of variables, it would be a product of the power sums in these multiple variables. And similarly for the Schur function, so we now get products of Schur functions in the various variables. We have a scalar product. And again, these are orthonormal with respect to, or orthogonal, I should say, under the Hall inner product. And if you look at the Frobenius characteristic map for the trivial representation of this uniform block permutation, you can see that you get some sort of product of Schur function. One thing that we also proved is that these coefficients that we got by expanding the characters of the uniform block permutation in terms of the characters of the maximal subgroups, you can actually get them by looking at these inner products of these generalized power sum symmetry. And similarly, the characters of the uniform block permutation you can get by taking the inner product of the Schur function with a p, with a power sum symmetric function. And the last thing I would actually like to mention is that by doing all this, we actually now cycle back to the problem that I started out with, namely this plethysm problem. Namely, so now let's look at the representation, the irreducible representation of our uniform block permutation algebra. And let's restrict it to Sk, so the symmetric group Sk. And if we want to know what is the multiplicity of an irreducible of Sk in there, then this is in fact given by this expression. And this is now actually in terms of the usual symmetric functions. So as you can see on the left-hand side, we have a product of plethysms of Schur functions. And then what we do is we take this product of plethysms of Schur functions and we take the coefficient of S mu in there. And that exactly gives you the multiplicity of this restriction. And this is precisely the reason why we got excited about this, is because now we have a representation theoretic way of hopefully handling this plethysm problem. So thank you very much for listening. And if this was a little bit much, I just want to give you two takeaways from this talk. First of all, plethysm is really hard. And then the second one is sometimes even when you have a hard problem, if you take a random walk, you learn a lot of very nice mathematics on the way, and you can explore a lot of new things that you didn't know before. And sometimes you actually cycle back to your original problem. So thank you very much.
Okay, well, thank you very much for your very nice talk. And are there any questions or comments? I think everybody is very tired.
Yeah, I know.
It's been a very
This
long
is like
day.
the last day.
Yeah, it has been a very long day. And